Welcome to this video where we are going to continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular in this talk we are going to focus on components contained in chapter 2, which covers stability properties of dynamical systems and corresponding Lyapunov characterizations. So here I will only give the main concepts and you will find more detailed results in the book and in particular in this chapter. Okay, so simplest setting is to consider autonomous systems of the form x dot is equal to f of x with a corresponding initial condition, and we are interested in the solution x of t for t going to infinity. So are we going to converge to a particular value, or how does the solution look like? And recall from the definitions in chapter 1 how we defined an equilibrium. Namely, an equilibrium is defined through x dot equal to 0. So we are looking for function value xe such that f of xe is equal to 0. Then this xe, the equilibrium, is a special solution of our differential equation, namely it is a constant solution. And with that, with the definition of an equilibrium, we can look at stability notions. So here, for the sake of the definition, we consider again our dynamical system x dot is equal to f of x, and without loss of generality, we assume that xe, the equilibrium, is at the origin. Then our first definition here is Lyapunov stability. How is that defined? Well, we say the equilibrium, the origin, is stable if for any epsilon bigger than 0, there exists a delta, which might depend on epsilon, that's bigger than 0, such that if our initial condition is less or equal, in norm, less or equal to delta, then our solution for all t in norm needs to be less or equal to epsilon. So looking at this illustration down here, meaning if we are starting with our initial condition here in this delta ball, then our solution for all times t needs to lie in this epsilon ball. So here in this case, if we look at this solution here, it would satisfy this condition. And if it satisfies that for all t and for all initial conditions in this delta ball, then we would have stability. Next definition, instability. Well, that definition is simple once we've understood stability, namely an equilibrium, the origin is unstable if it is not stable. And the next definition, attractivity. So this then focuses on the limit for t going to infinity. So if we start again in a neighborhood of the equilibrium, meaning the norm of x0 is less than delta, and if we now let t going to infinity, then we say that the origin is attractive if we converge to 0. And the final definition here is asymptotic stability, namely if we have the properties of stability and attractivity, then we say the equilibrium is asymptotically stable. And note that attractivity indeed does not imply stability, and we have to assume stability and attractivity to conclude asymptotic stability. Okay, so that's just potentially an abstract definition. Let's look at very simple examples. So simplest examples we can consider here would be the three differential equations highlighting the different cases. X dot equal to 0 has as a solution x of t is equal to x0, so constant. This is an example of a stable equilibrium at the origin, but it is not attractive. X dot is equal to x with the solution e to the power t times the initial condition. E of t is increasing, so we will leave every epsilon neighborhood. Doesn't matter how close we start to the origin. If we want to start there in a neighborhood of the origin, meaning this would be an example of an unstable equilibrium. And then the last example, x dot is equal to minus x, providing the solution x of t is equal to e to the power minus t times x0. Here we see that for t going to infinity, this is decreasing to 0, which means we have attractivity, and this additionally is always less in norm, less or absolute value less or equal to x0, giving us also stability, and we obtain asymptotic stability. These are, of course, very simple examples, and here we rely on the solution to conclude properties such as stability, instability, and asymptotic stability. An alternative way, which does not rely on the explicit knowledge of the solution, is through Lyapunov functions. So how can we characterize stability through a Lyapunov function? Well, it can be shown that, again, under the same assumptions as before, in terms of dynamical system and equilibrium at the origin, that if we can find a continuously differentiable function mapping from Rn to the positive numbers or positive reals, and if we can find k-infinity function alpha 1, alpha 2, such that these two conditions here are satisfied, then we can conclude here in this case even global stability. So the first condition here is a technical condition where the upper bound here essentially ensures that V of 0 is equal to 0. So we have a minimal energy at the origin. And the lower bound with alpha 1 ensures that we have a radially unbounded function, meaning if x goes to infinity in norm, then also our function v goes to infinity. And this condition is, I would say, the more difficult condition to verify. It's the decrease condition, showing that along solutions, the function v is monotonically decreasing, or at least not increasing. And while it looks like it depends on the solution here, the actual expression which we need to evaluate that is independent of the solution, meaning we can simply calculate the gradient of the function v, multiply it with f of x, and verify that this inequality is satisfied for all x to be able to conclude stability. With a slight variation, we even obtain asymptotic stability. Namely, if we are not demanding that the inner product here is less or equal to 0, but that it's actually less than 0 for all x unequal to 0, defined here through a positive definite function, then we can conclude asymptotic stability. Okay, and the interpretation was already given before, but it is essentially this energy interpretation of a Lyapunov function showing that we have a global minimum at the equilibrium, and then along trajectories the function v, or the energy, is decreasing meaning that sublevel sets are forward invariant, and if we always have a decrease, not just less or equal to 0, then we will converge to 0, giving us asymptotic stability. Yeah, and as mentioned, that is kind of a generalized energy function with very specific properties along the solution without explicit knowledge of the solution. Finding V, of course, is also difficult or non-trivial in general, but in many cases a lot easier than finding the explicit solution. These are, as presented here, are sufficient conditions, meaning if we have a Lyapunov function, then we can conclude stability or asymptotic stability. There are also converse results giving necessary conditions, meaning if we know that our system is stable or asymptotically stable, then there also needs to exist a corresponding Lyapunov function. Yeah, as mentioned before, here we focused on this very simple dynamical system, autonomous, but we can also extend that to time-varying systems. Here we have focused on characterizations of stability and asymptotic stability, but we can also define Lyapunov functions which guarantee exponential stability or which guarantee instability. Yeah. Finally, kind of here, these are global results because it needs to be satisfied for all x in Rn, but this can also be restricted to local results, giving local stability and local asymptotic stability. And as a simple example, one can try to verify with the quadratic function here that v of x being equal to x squared is a Lyapunov function for the system x dot is equal to 0, characterizing stability, or asymptotic stability for x dot is equal to minus x. Okay, so this covers the basic content contained in chapter 2 in terms of stability. Next video will focus on linear systems and linearization.